Okay, so first section we're going to look at this week is 7.5, and it's on what we call sum and difference identities. There's going to be 6 main trig identities we look at in this section. Sine with a sum, cosine with a sum, tangent with a sum. And then we'll look at sine with a difference, cosine with a difference, tangent with a difference. And you'll be like, well, what do I mean by sum and difference? That right there is the sign of a sum. That's one of the 6 examples I just mentioned. And the question is what's on the left and what's on the right the same? What do we think? Do you think sine of x plus 3 in parentheses is the same as sine of x plus sine of 3? Any thoughts? Caleb?
Yeah, because it's like you're distributing sine.
All right, so it's like you're distributing sine. So I can definitely see where you would think that. Let's graph it just to see what it looks like and see if it looks the same. So we've got sine of x plus 3 and sine of x plus sine of 3. Now before I hit graph, when you do transformations, is there a difference if you put something inside the parentheses or it's outside parentheses? Yeah, it does make a difference. If you have like this versus this, whether it's adding a number inside the function or outside the function, it does make a difference. This is a left phase shift, that's horizontal. That's a vertical shift. So just by the structure of it, you probably can get an idea that they are going to look different. And there's sine of x plus 3, shifted 3 radians to the left. And there's sine of x plus sine of 3, which is shifted up a little bit. Sine of 3 is a pretty small number, so it's a vertical shift up, but it's only up a very, very small amount. And if you look closely, the red one is a little higher than the blue. So yeah, they're not the same. So distributive property does not work. You can't distribute a function like that. If you have a number on the outside, absolutely. Not a function. So how could we deal with something like that? Well, I'm going to start off by showing you the formula for how you deal with it with cosine. And then from there, we can build up to how would you deal with it with sine and tangent. So the first one I'm going to give you, and I'm just going to give it to you, it's the cosine of a difference. Okay, you definitely cannot distribute cosine. But what you can do is what's on the right-hand side. Now, the reason why that works, that's a little complicated. The proof is in your book. I've gone through the proof before, but it takes about 15 to 20 minutes to go through it. And honestly, the benefit of going through the proof, I don't think is worth the amount of time it would take to go through it. So I'm going to give you this one, and then from this one we can build some other things from it. Okay, so the cosine of a difference is, I call alpha the first, and I call beta the second. So cosine of the first times cosine second plus sine first, sine second. Not that hard to remember on its own, but once I show you the cosine of a sum, and then the sine of a sum, and the sine of a difference, they're all like the same. They're all very, very, very similar looking. So it's kind of hard to remember them. It's definitely a good thing to put on your reference sheet. Okay, so again, proof's on page 409. And then the proof has to do with these pictures, which, again, I really don't want to spend the 15 minutes to go through it. So, where could you use cosine of a difference? Well, what the sum and difference identities allow you to do is find the exact value of a problem like that. Okay, so up until this point, we only know how to find exact values of any angle that's a multiple of 30 or 45. Now with these formulas, you're going to be able to do the 15s. So really, anything that's a multiple of 15, which covers all the 30s and 45s as well, you'll be able to do now. The trick is you have to write it as either a sum or a difference. This one we'll do as a difference because that's the formula we have. And the two numbers that you use have to be multiples of 30 and 45. So you can use numbers like 30, 60, 90, 120, 45, 90, 135, 180, 225. Any of the numbers I just said you can fill in here. So can anybody think of a way you can write 15 as a difference of two numbers, and the numbers have to be multiples of 30s and 45s?
45 minus 30.
Yeah, you can write it as 45 minus 30. And the reason we're going to use 45s and 30s is because when we fill it into the formula on the right, we should know how to find all those answers. We can either use unit circle trig, or the easier way is just to memorize some certain answers. So we're going to start with cosine of the first, cosine of the second. So cosine of the first, cosine of the second. And then we've got plus sine of the first, sine of the second. Sine first, sine second. Now, in calculus, it's a really good idea to just have all the 45s and 30s memorized, sines and cosines. But if you don't, what you can do is you can type it in and see what it comes out to. And then hopefully, when you see the decimal, it'll kind of jog your memory of what the exact answer is. Okay, cosine of 45, you're going to get 0.707. Does anybody remember what that is as a fraction? It has a square root in it. What square root did we use a lot when you deal with a 45, 45, 90 triangle?
Square root of 2.
Yep, and that's the square root of 2 over 2. Okay. If you didn't know that, you could go through all of unit circle trig. You could draw your circle, make your triangle, label the sides, and then cosine is the x value of the coordinate for that point. But that's going to take forever. So if we just have it memorized that 0.707 is square root of 2 over 2, we're good. Okay, cosine of 30, you could do the same thing. You could draw your picture, do all that stuff, but I'm hoping once you see the number, it'll remind you of it. Does anybody remember what square root comes up when you do the 30, 60, 90? It's not square root of 2, but yeah.
Square root of 3?
It's square root of 3. And does anyone have a guess what you can do with the square root of 3 to get 0.866? Yep.
Divide by 10.
Yeah, it's the square root of 3 over 2. Square root of 3. Oops. And divided by 2 is 0.866. Now the sine of 45 is the same as the cosine of 45. Those are cofunctions of complementary angles. If you don't remember it, not a big deal. But if you type in sine of 45, you would get 0.707. So it's also root 2 over 2. And the sine of 30, if you type that in, that is 1/2. So if you have these memorized, this step you can do in about 5 seconds. If not, it might take a little longer. Okay. And now we've got two products, but the nice thing is everything already has the same denominator, which is going to be important at the very last step, okay, when we do addition. So let's multiply. Square root 2 times square root 3. It's the square root of 6 over 4. And in the second part, square root of 2 times 1 over 4. And now just put it all with a common denominator. Square root of 6 plus square root of 2 over 4. That's the exact answer for the cosine of 15. That's how you get it. And we can check it. Very easy. Okay, there's the cosine of 15. And let's take square root of 6 plus square root of 2. Since I didn't put parentheses, I'll just do it in 2 steps. And then divide by 4. So, exact same answer. Yeah.
You can't simplify it anymore.
No, that's all you can do. If you could reduce one of these square roots in the top, like if the top was a square root of 12, then maybe you could do something with that, write it as 2 square root 3. But you can't simplify the square root of 6 or the square root of 2. And you definitely can't reduce 6 and 2 because the 6 and 2 are under the root, so you just have to leave it. Okay. Any other questions on that? Okay. And there's other ways to get 15. If I had taught you the sum formula, which we'll do in a minute, you could probably figure out a way to write 15 as a sum using a negative number and a positive number. Multiples of 30 and 45. Sometimes it just takes a little practice to figure it out, but you can do it. All right, so this is less numeric, and this is more of a verify. Okay, so it's a proof, but it's a very structured proof. You don't have to guess at what to do. It's the cosine of a difference. There's the first, there's the second. So just fill it in exactly like we just did this problem, except instead of a 45 and a 30, you're going to use a pi over 2 and a theta. Those are the two things. Okay, so can someone remind me, what's the first part of the formula before the plus sign? Oh, yeah, Liam?
Cosine pi over 2 times cosine theta.
Yep, cosine of the first times cosine of the second. So there's cosine of the first, cosine of the second. Now, can somebody remind me what the last part is, Jane?
Sine of pi over 2 times sine of theta.
Sine of the first, sine of the second. Now, let's take the cosine, or actually, does anyone remember what the cosine of pi over 2 is? It's the same as the cosine of 90. Think about your graph of cosine. Starts here, comes down and goes up. These points that I'm labeling, these are all the quarter points in the period. So now looking at that picture, anyone remember what the cosine of 90 is? Yep. That's the cosine of 0. The cosine of 0 is 1, and then the cosine of 360 is also 1. But 1 does come up, and it will come up in a little bit. Yep.
0.
0. Yeah. This is 0, pi over 2, pi, 3 pi over 2, and 2 pi. So the cosine of pi over 2 is 0. So what's going to happen? 0 times anything gives you 0. So this whole part cancels out. So now all you're left with is sine pi over 2 times sine. Well, let's look at the graph of sine. Marking all the quarter points. And if you're looking for pi over 2, what would be the sine of pi over 2? Yeah, it would be 1. Pi over 2. 0, pi over 2, pi, 3 pi over 2, 2 pi. Pi over 2 has a sine of 1. So this turns into 1. So the only thing I'm left with is 0 plus 1 times sine. Well, 0 plus anything, we don't even need to do 0. And then 1 times sine. All you get is sine, which is exactly what you were supposed to get. Okay, so for some reason, people have trouble with those on the test, but that's very, very similar to one you're going to see on the test. Maybe the one on the test will be a plus instead of a minus. Okay, but I'm going to show you that formula right now. Okay, so that's how you prove an identity that's a sum or a difference. You plug it into the formula. Okay, that formula right there. Okay, any questions on that? So most people like these identities better than the ones we did last time because you don't have to guess at what to do. You just plug it into the formula, and that's it. As long as you know the formula. Okay, let's try this one. Cosine of pi minus theta. So my argument is that the cosine of pi minus theta is exactly the same as the negative cosine of theta. And why would you want to know that? Well, what's on the right is simpler. So in calculus, if you had to do something with this, I would rather work with the thing on the right than the thing on the left. Right. Can anyone set up my identity for me, just plugging in what we need to, and then we'll go through it from there. Yep. Good.
The cosine of pi times the cosine of theta
So cosine pi, yep. Cosine theta
plus sine of pi times sine of theta.
plus sine pi sine theta. Yep. Very good. Now, to figure out what's the cosine of pi, I'm just going to go back and look at my graph. Wherever it is. So cosine of pi, 0, pi over 2, pi. Cosine of pi is -1. All right, so let's do that. So cosine of theta, you can't do anything with that. Okay, sine of pi, let's go back and look at our graph. Somehow I deleted the page, but I think it's okay now. All right, so sine of pi, 0, pi over 2, pi. Sine of pi, 0. If you don't know that, you could type it in on the calculator and get it that way too. So on the test for a proof or a verify for a problem like this, that's what I would be looking for you to show me. Show me you plugged it into the formula. Show me how to get the -1 and the 0. And now 0 times that cancels out. -1 times cosine. There's your negative cosine. And that's exactly what they wanted us to get. Okay, questions on that? Excuse me. Thank you. All right, so now we did the cosine difference. We're going to look at the cosine sum. Okay. Since I've given you the first formula, that one was really hard to prove. Now that we have it, we can use that to figure out the cosine sum formula. But you also need to remember these two facts. That the cosine of a negative angle is the same as just the cosine of the angle. You could try it. Take the cosine of -10, take the cosine of +10. You're going to get the same thing. That doesn't quite work with sine. With sine, you can't just get rid of the negative, but what you can do is move it in front. Okay, so just keep those two ideas in mind. Those are called even-odd identities. I think we talked about them a while ago, but I'm just reminding you of them. Okay, so let's see if we can figure out cosine of a sum. Well, right now we know cosine of a difference. So if we're going to use that to figure it out, we need to rewrite a sum as a difference. Anyone think they could tell me how I could rewrite what I have right in parentheses, alpha plus beta, as a difference? And this isn't anything like super fancy. This is just basic kind of subtraction rules that if you do this, it would turn into a positive. Yeah?
Subtract negative.
Okay, so how would you, can you tell me how to write it?
Alpha minus negative beta.
Exactly. Now, since you've written it as a difference, you can go back and use the cosine difference formula. There's your first. The difference, or the thing that's changing, is that's the second, negative beta. So now let's just go through and see what happens. So it's cosine, cosine. And then is it a plus or a minus? That comes next. Well, Dylan, do you remember from the formula?
It's a plus.
It's a plus. Yeah, it's not too bad to remember with just one formula, but once you learn them all, then it's kind of confusing. Is this the one that uses the plus or the minus? So just got to keep it straight. So cosine, cosine, sine, sine. And now we have some negatives inside the argument, but the two formulas right here will help us to get rid of the negatives inside the argument. So, cosine alpha, that's just going to stay the same. How about cosine negative beta? What can I do with the negative in front of beta? Yep, Jamie.
You could just take it out.
I can just get rid of it. Doesn't make a difference. We can just totally get rid of it. Now the next part, before I write anything, I'm going to look at the end. I have sine negative beta. Can I just get rid of the negative on the beta? Yep.
How do you put the negative before sine?
Yeah, I can take the negative and I can put it in front. So it's like multiplying sine by negative sine beta. So it's really going to be a positive. That's a negative once you put the negative in front. Positive times negative, negative. So now you have sine alpha, sine beta. And there's your formula for the cosine of a sum. Very, very similar to a difference. The only thing that changes is the sign.
Why can't you just get rid of the negative in the sum?
That's an identity.
Oh.
It's what we call an even-odd identity. I mean, I could just show you with a quick example. This is not a proof at all. But if you take the cosine of negative 12, I just picked a number, cosine positive 12, they come out exactly the same. There is more of a proof why, but we're not going to go through it right now. So any questions on the formula for the cosine of a sum? All right. So now we should be able to do something like that. Anyone think how you can write 75 as a sum, and the two numbers that you use have to be multiples of 30 and 45. So you can't say like 65 plus 10. That's not going to work. Yep. Yeah. And if you're wondering, what if I did 30 plus 45, you'd get the same answer. If you couldn't think how to do it as a sum, you can write 75 as a difference. If you think about it a little bit, there is a way to subtract two numbers and get 75. Anyone know what it would be? What minus what would give you 75?
You do 45 minus negative 30.
So you could, that's kind of like just doing what we did before. You could think of it as 45 minus negative 30, but you can actually do it without minus a minus. You can take a positive number minus a positive number and get 75. Yep. So the two numbers that we use both have to be multiples of 30 and 45. But that's a good guess. Yeah?
135 or minus 60.
Yeah, exactly. If you took 135, which is a multiple of 45, 60, which is a multiple of 30, if you subtract the two, you get 75. So you could technically do cosine 75 as a difference problem if you forgot the sum. Anything you can do as a sum, you can do as a difference. That's kind of the point. All right, so now let's go through cosine, cosine. And then we know it's sine, sine. Only thing we have to remember now, is it a plus or a minus between them? Yeah, it's a minus. With the cosine identities, it's always the opposite. When you see a plus, the formula has a minus. When you see a minus, it has a plus. Unfortunately, with the sine identities, it doesn't work that way. It's actually the same. If you see a plus, it's a plus. If you see a minus, it's a minus. That's why it's a little confusing to keep track of. All right, so let's go through. Cosine of 45, what is that as a fraction? Yep.
Square root 2 over 2.
Square root 2 over 2. Cosine of 30. We did that one earlier, I think. It was square root 3 over 2. Sine of 45, what is that one? Yeah. 2 over 2. And the sine of 30, it's the only one that comes out as a rational number in this problem. Yeah. That one's a half. Okay. A lot of these problems usually end up being something like a square root of 6, a square root of 2, and divided by 4. Sometimes it's plus, sometimes it's minus, sometimes they're negative, but that's usually what it ends up being. So square root 2 times square root 3, square root 2 times 1, put your minus in the middle, and it's all divided by 4. Any questions on that? So now you should be able to figure out the cosine of any angle that's a multiple of 15. I think the hardest thing is just figuring out how do you write it. How do you figure out, like if let's just take one more and see if we can just write it. Let's do 105. 105 is a multiple of 15. How can you write 105 as a sum or difference of two angles that are multiples of 30 and 45? Yep.
45 plus 60.
So 45 plus 60. Perfect. So if you were going to do this, you could use 45 and 60. Did anybody think of a different way to do it? How about as a difference? Besides 45 minus negative 60. You can do that. But how could you write 105 as a difference? Yep?
135 minus 30.
Yeah. Okay. So no matter which way you do it, you're going to get the same answer. Yep. Just have to figure out how to write it. And every multiple of 15, I guarantee you can write somehow. Just takes a little practice. Right. So there's the cosine. Let's take a look at sine. Now, to help you a little bit, I'm reminding you of a fact about sine and cosine. Sine and cosine are basically the same graph. They're just phase shifts of each other. Remember, when we graph just the basic sine function and the basic cosine function, and I need to adjust the window a little bit. If I do zoom 7, this will look a lot better. The two graphs you're about to see are almost the same graph, except one of them is shifted 90 degrees away from the other. If you took the graph in red and just shifted it 90 degrees to the right, you'd get the graph in blue. Or you could shift the one in blue 90 degrees to the left. That's what this fact is saying right here. Sine and cosine are phase shifts of each other. And since they are, we can use that fact to figure out the sign of a sum. So what we're going to do is we're going to use the cosine, we're going to use one of the identities we already know to figure out the sign of a sum. The one we're going to use is the cosine difference formula. So the sine of something is the same as the cosine of pi over 2 minus the something. What's the something we're using? What's in that box right there? So basically plug that in for theta. So we're going to replace theta with alpha plus beta. Okay, and see what we get. So it would be the cosine of pi over 2 minus the something. This time the something is alpha plus beta. So when I write alpha plus beta, what do I have to be careful that I put here? I have to put parentheses because it's minus the whole thing. Minus the whole thing. Okay, and at first when you look at that, you might be like, that doesn't really help. But if we regroup it a little bit, this is going to work. Okay, so first thing I'm going to do is I'm just going to regroup it by distributing out that negative. Okay, so let's start with cosine pi over 2 minus alpha. And then I'm going to put minus beta. So what I really just did is I kind of separated into first and second. That's going to be my first. That's going to be my second. So now we're going to use the cosine difference identity. First, second. So cosine, cosine, plus sine, sine. Fill all that in, and then it's going to simplify nicely. So cosine of the first times cosine of the second. And if you're like, well, wait, why didn't I use the negative on the beta? It's what comes after the minus sign. Whatever's before the minus sign is the first. Whatever's after the minus sign is the second. So cosine, cosine. And then sine of the first. Sine of the second. And with cosine, you always put the opposite of what you see. We had a minus, so we're going to put a plus. Now, first thing I want to look at is this. The cosine of pi over 2 minus alpha. Look up above. What is the cosine of pi over 2 minus alpha equal to? Yeah? Yeah. The cosine of pi over 2 minus anything is just the sine of that thing. So this whole thing is just the sine of that thing. It's sine alpha. Cosine beta, you really can't do much with that. Plus, now, I didn't write this one down, but what do you think the sine of pi over 2 minus alpha is the same as? Using basically this concept right there. The sine of pi over 2 minus alpha. Yep. It's the same as the cosine. Okay, I kind of explained you could shift either one 90 degrees to get the other. Well, now you're looking at it from the other perspective. Sine of pi over 2 minus alpha is the same as cosine alpha. And then sine beta, you can't really do anything with it. There is the formula for the sine of a sum. It's sine, cosine, cosine, sine. So this is where it gets a little tricky, because the cosine ones, it was always the 2 cosines first, the 2 sines second. Now you got one of each. A sine, cosine in the first part, cosine, sine in the second. And if you're like, well, why did I switch the order? Why did I write sine, cosine, and then cosine, sine? It's because I wanted to keep alpha, beta, alpha, beta. I just wanted to keep that order. So sine first, cosine second, cosine first, sine second. Okay. Any guess what's going to change in that formula to give us the sine difference? This one I'm not going to go through the whole proof, but any thought what's going to change? Yeah?
The plus is going to be a minus.
Yeah, the plus is going to be a minus. It's still going to be sine first, cosine second, cosine first, sine second. But between them, you have a minus. Okay, so point of these formulas isn't really to memorize them. Put them on a reference sheet, so when you need it, you just look it up. Okay, so now with these two formulas, you should be able to do the sine of any angle that's a multiple of 15. Write it the same way you did cosine. Figure out how to do if it's like 75 plus 30 or whatever, whatever you need to do. 30 plus 45. And then use either that formula or that formula. So is there any questions on how you would do like sine 75 if I asked you how to do it? Okay, so we'll skip going through numerical examples with sine. So you've got the two formulas. Okay, the tangent ones aren't used as often. They're much more complicated, I think, to remember. So in a pinch, if I really had to, does anybody remember what tangent is the same as if you write tangent as a fraction? Yeah? It's sine over cosine. So if you really wanted me to find the tangent of 15, it's going to take a while, but what I could do is I could do the sine of 15, get that answer, and then divide it by the cosine of 15. And if I really had to, that's how I could do it, because I know the sine and cosine identities. But there is a shortcut. I just think it's kind of hard to remember it. If you want to do the tangent of a sum without doing the sine and the cosine, that's how you could do it. Okay, and we're getting to the point where there is a proof of that, but I'm not going to go through it. Okay, it says it just takes a while. So all I would want you to be able to do is to find like the tangent of 15. So you write it as 45 minus 30, and then you fill in all the 45s and 30s. But what's going to come up with tangent, root 2 over 2 comes up a lot with 45s. Root 3 over 2 comes up a lot with 30s and 60s. But with tangent, you're going to see a number like this. Let's do tangent of 30. That's root 3 over 3. So when you plug in 30s and 60s, you're going to see root 3 over 3 come up a lot. Okay. That's just root 3. That's all. Take the square root of 3, it's 1.73. So square root of 3, root 3 over 3. Those are the two numbers you're going to see come up here. Something else you might see come up, kind of a nice one, if you use a 45, the tangent of it is 1. So whenever you can use a 45, the answer comes out very nice.
I'm not asking you to go through the proof, but where does the whole number 1 come from in that?
Honestly, I would have to look at the proof myself and see. I've never gone through the whole proof in detail of this one. So I'll have to check it out and see. In fact, I don't even think it's in your book. No, your book doesn't prove it. Actually, problems 47 and 48 in the homework are questions that ask you to prove it yourself. So your book doesn't show you how to do it. But if they're asking you to do it as a question in the homework, chances are it's not that crazy to go through. I would just have to think about it a little bit. I mean, one thing I could do is I could try doing it this way. I have a feeling that's probably going to be a little messy to take the sine and divide by the cosine. But there might be a very, very simple way. I'm just not thinking of it off the top of my head.
In unit circle trig, wouldn't a 45 degree, wouldn't a 45, 90, the tangent opposite or adjacent have the same two values? Over?
Yes.
So that's why it comes out to 1.
That's why it comes out to 1. Yep. Yep. Because when you divide opposite and adjacent, it's an isosceles triangle. Yep. Exactly. And then following kind of the same pattern, when you change from a sum to a difference, the only thing that changes is the signs. And you could probably, again, you could figure out why that is the way it is the way it is. If you went online and you just type proof of tangent difference identity, I'm sure it would come up right away. But before I look it up online, I'd be interested just to see if I could figure it out without looking it up. Okay, so everybody have those two. So now you have 6 different identities. 3 for sum, 3 for difference. Okay. So the next group of identities we're going to look at have to do with this idea. If you have a 2 inside or outside, totally different. You put it inside, that's a horizontal stretch or compression. Put it outside, that's a vertical. So I'm not going to graph it, but hopefully you can see those are not the same. So, how can you get rid of that 2? Okay, when we have trig equations, we don't like to have numbers in the argument. We want it to just be a letter. So you can't just take the 2 and put it out front. That doesn't work. But there is something you can do. And I'm going to show you what you can do. I'll give you a list of these formulas in a second. And the first one I'm going to give you, we're going to prove it. I think this will be one of the last proofs I go through today. Just because if I prove everything, it's going to start taking a long time. All right. So I want to prove that the sine of 2 times something is the same as 2 sine cosine. So I'm going to start with that. And can somebody tell me, how would you get 2 theta as an answer? Like, what would be the calculation you would have to do, and the answer would be 2 theta, besides 2 times theta. 2 times theta would be 2 theta, but what's another way you could get 2 theta as an answer? Or 2x. Like, what would be a calculation in Algebra 1 you would do, and the answer would come out to 2x? Think about when you combine like terms. Theo?
Theta plus theta.
Yeah, think of it as theta plus theta. Theta plus theta is 2 theta. And why would I want to think of it as sine of theta plus theta? Why does that help me a lot now? Yeah?
So now you have alpha and beta.
Yeah, that's the sine sum identity. So let's just go back and look at what the sine sum identity is. Sine, cosine, cosine, sine, with a plus between them. All right? So, sine, cosine, cosine, sine, with a plus between them. Now, fill in first and second. This is first, that's second, that's first, that's second. But look at first and second. They're the same. So you have first, second, first, second. So you have sine times cosine plus cosine times sine. What's the difference between sine times cosine or cosine times sine? Yeah? They're the same. It's like doing x times y plus y times x. It's the same thing. So you have a sine times a cosine. You have another sine times a cosine. So you have 2 of the sine times cosines. And that's the proof of why sine 2 theta is the same as 2 sine cosine. And that's called a double angle identity. So a double angle identity is a formula that gets rid of a number that's in front of the argument. For the sine, there's generally one that they use, and that's it. For cosine, there's a couple. That's the first one. If you can just remember that one, you can figure out all the other ones. Now, that might look kind of like something we've done before. If you're thinking of, I'm just going to put it off to the side, sine squared plus cosine squared equals 1. That's not what that is. That's cosine squared minus sine squared. That's totally different. But if you use this, you can get the other version of it. For example, if you take cosine squared and subtract sine squared, bring it to the other side. Cosine squared is 1 minus sine squared. If you replace that with that, because that's what cosine squared equals, you get that. You actually get 1 minus sine squared minus sine squared. That's minus 2 sine squared. So you could write it that way, or you could rearrange the Pythagorean identity I just showed you and instead plug in for sine squared and get something that's kind of similar. So if I was making a reference sheet, if I had enough room, I would put all 3 of these on it. If I didn't, I would just put the first one and remember the Pythagorean identity and how I can get the other 2 if I need them. Those are the 2 that we use most often. Okay. I'm going to give you the tangent one. Honestly, on the test though, I'm not sure that there's going to be any problem with tangent 2 theta. But since I'm giving you the double angle identities, I'll give you all of them. But I wouldn't worry too much about tangent 2 theta. If you like trig and you like trying to figure out where things come from, that would probably be a good exercise to do. Think through it and figure out how does that formula even come up. You know, figure out the cosine one first, and then see if you could figure out the tangent one. Sometimes before I dive into figuring out something like that, I like to know like what level of difficulty it's going to be. Sometimes you think something's going to be really easy. Oh, I'll sit down and figure it out, and then you look and it's like a 6-page proof to do it. So I would do a little research if you want to figure it out. Make sure it's not something that's really crazy to figure out. Okay. So what the double angle identities are going to allow us to do is a problem like this. This problem says to rewrite using only sine and cosine. Okay, so I'll help you with the first one, and then we'll look at one that's a little more complicated. This part is fine. That part already has a cosine. There's no number in front of it at all, so just leave that alone. And by number in front, I mean right there. The next part, that's not good. We have a number in front of the x, sine 2x. I'm going to look up my formula, and I'm going to write it as 2 sine x cosine x. And technically I'm done. I've rewritten it so the problem only has sines and cosines now. There's no 2's in front of the x's. The only thing they could do if they wanted is they could factor here. Since there's a cosine in both parts, they could factor it out. Actually, there's a 2 and a cosine in both parts, so you could factor it out. Technically, you could write your answer like that. The directions did not say to factor it. I'm just showing you that in case you get a multiple choice question where they do it. Hey, any questions on that one? All right, let's look at one that's a little bit harder. This one says sine 2x plus cosine 3x. And I'm saying I'm only going to go up to a certain point with this problem because tomorrow I'm really going to show you how to finish it. Okay, so I'm just going to get it up to a certain point. All right, so the trick here, you have to get everything so it's just sine x's and cosine x's. No 2's in front of the x's, no 3's. The first part is relatively simple. 2 sine cosine. The second part, not so simple. Anyone have a thought about how you can rewrite 3x to kind of break it down? Think about how would you have gotten 3x as an answer by combining like terms. Sam? Yeah, think of it as 1x plus 2x. The higher the number is in front of the x, the worse the problem is. 3 is a little bit worse than 2, but it's nowhere near as bad as a problem with like a 5 or a 6. I wouldn't even give you one like that. Okay. Now, look at what we have right there. The cosine of a sum. So now use your cosine sum identity. First, second. And what that's going to do is it's going to split it apart. This 2 sine cosine is just going to kind of hang out in front for most of the problem. Cosine of a sum. Okay, so if we go back, look up our formula. Cosine of a sum, cosine, cosine, minus sine, sine. So cosine, cosine, minus sine, sine. So, first, second, first, second. Okay. Any question on that step? And it's better, because now we don't have any 3's left in the problem. We've got some 2's, but we know how to deal with some of that. All right. So what I have to deal with now is this and that. Everything that doesn't have a box around it is perfectly fine. So I'm going to leave that. Now, what's a little tricky about dealing with that first black box is it's cosine 2x. Well, you've got a few options for how to rewrite a double angle formula. I'm just going to give you a hint. We're going to use the 1 minus 2 sine squared. We're going to go with that one. Okay, which one you go with, and it just takes a little practice to figure it out. But just trust me on this one, just for the purpose of kind of getting through the problem, and I'll show you what happens if you use that. So 1 minus 2 sine squared. So it's going to become 1 minus 2 sine squared x. Cosine x. Any question on that? And I really need to leave that in parentheses because that technically is a distributive property. Cosine 2x is being multiplied by cosine x. So whatever you change it to, it's all multiplied by cosine. Okay, and what about at the end? What does sine 2x turn into? Yeah. Yeah, that's the only one that I usually remember. The sine double angle, 2 sine cosine. Just because it's kind of easy to remember. So 2 sine cosine times that other sine we had at the end. So if we wanted, what we could do, just to kind of simplify it a little bit, is just make it sine squared. Any question on that? Right, now from here, I'm just going to try to combine some like terms. I'm going to distribute some things out because I need to take care of that. This 2 sine cosine just hanging out in front pretty much the whole problem. Okay, let's distribute that out and see what we get. So we're going to get 1 times cosine minus, and this is what I'm hoping you kind of notice with what's at the end, 2 sine squared cosine. Two sine squared cosine, 2 sine squared cosine. Now I've got something I can combine together. Minus 2 sine squared cosine, minus another 2 sine squared cosine. Okay, how much is that? If we combine those together. Yeah?
-4.
Yeah, it's a -4 of whatever you're combining, sine squared cosine. Now the book does a lot of things all at once in this step. I'm gonna do one thing at a time because I think it'll, if you look back at it and I skip 3 steps, it's gonna be kind of like, what did he do? So I'm trying to make it so if you do look back at it, you can see each step. Minus 4, sine squared, cosine. Now, you might be looking at it and be like, oh my god, there's way too much stuff here. But what does everything have in common that you could factor out? Yeah?
It all has cosine.
It all has a cosine, and watch what happens if you do that. Something I mentioned at the very beginning of class is going to happen, and this equation, this thing is going to turn into a certain type of equation. So let's factor out a cosine. That leaves me with 2 sine x plus 1 minus 4 sine squared x. Now, if you're still looking at it and you're like, I have no idea what he's talking about inside parentheses, let me reorder what's inside there and see if you recognize what it is. I'm going to write the sine squared first, the sine x term second, and the constant last. Now, does anybody recognize what's inside the parentheses now? Yeah?
Quadratic.
That's a quadratic equation. So at that point, I said that's where we're going to stop, because now you would use the quadratic formula to solve that. That's what I'm going to do tomorrow. That's kind of a hard one. There's a lot of rewriting and combining like terms. It's not a very easy question to completely understand the first time. Okay. So any questions just up to that point? All right. So, actually, those are all the answers, but don't worry about the answers. We're going to solve a problem kind of like that tomorrow. Okay. All right, so the last group of identities, again, not something you should really memorize, just put them on your reference sheet, are the half angle identities. Okay. I'm not going to do very much with these at all. I'm giving them to you honestly, so you have them if you need them next year. So if you need to look back at your pre-calculus notebook, if you're in calculus, they're in there. You don't have to really worry about these for the test. Okay, I'm telling you that right now. But when you take pre-calculus, these are kind of another classic group of identities, and if I just skipped them and didn't even give them to you, that wouldn't really be good. So what these identities do is they give you a few more options to calculate things. Let's say you wanted to figure out, I don't know, the sine of 45, and you didn't know it. Okay, you should, that's one you should memorize. But if you didn't know the sine of 45, what you could do is think of it this way, if it helped. You could think of it as 90 divided by 2. And then if you know the 90s, which usually people remember those a little better because they're zeros, ones, and negative ones, you could work backwards and figure out the sine of 45 if you knew cosine of 90. Okay. So again, don't worry too much, don't worry at all about those for the test. I'm just giving them to you so you have them. So now we've pretty much covered all the basic identities that you would cover in pre-calculus. The reciprocal, the Pythagorean, the tangent and cotangent. We did those last week. And then your sum and difference, your double angle, and your half angle. Are those all the identities? No, there's thousands of identities. But those are the ones that are pretty common. Okay. Any questions on those? All right. Okay, so that's the homework for tonight. So it's 1 through 5, 9 through 11, and then it kind of skips around 17, 18, 29, 31A. I think there's a 31, yeah, there's a 31 part B, you don't have to do it. And then 37, 41, and 45. Okay, that's all on page 417. Okay, so you got a little under 15 minutes, so if you have any questions, you could start, work on it a little bit. I can help you with anything. And then tomorrow we will finish chapter 7.